Welcome to the third lecture on the verified software toolchain, Verifiable C. And here I'm going to just show some examples in separation logic, how to represent data structures in separation logic. So there was a question asked during a previous lecture, how do you do doubly linked lists? So at the top of the slide we have singly linked lists with sort of the conventional representation in separation logic. P is a linked list representing sequence sigma if P is nil and the memory has the empty footprint. P is null, and sigma is nil, or sigma equals H con sigma prime and P maps to a record H comma Y, and Y is a linked list representing sigma prime. Okay, so suppose we have a doubly linked list, just an extra pointer in each record pointing backwards to the previous. It's not so hard to adjust this recursive definition to accommodate the back pointer. And one might do it like this. So N points to a doubly linked list representing the sequence sigma with back pointer P if, well, sigma equals nil and emp and n equals 0, the null pointer, or I think this might be right, or there's an H and a sigma prime and a Y such that sigma equals H con sigma prime and n points to H P Y. And then there's a doubly linked list representing sigma prime with back pointer n. So the rest of the list has a back pointer pointing at this object here. So the back pointer n of the rest of the doubly linked list is sitting right here pointing back at this object. So in general, it's just not that difficult to represent data structures. Here's another data structure. It's a linked list of strings in C. So a string in C is an array of characters of arbitrary length terminated by a null character. And when we want to represent this array of strings, we have to decide, are these string pointers shared with some other data structure, or is each string pointer owned by the linked list cell? Because there are different ways of programming this pattern in C, and we have to decide which way we meant. So suppose we mean that this string should be locally owned by the list cell. Now, how do we represent a string? Here's how we could represent strings. So the byte module is just the 8-bit modular integer arithmetic module from the CompCert C front-end specification. So byte.int is 8-bit integers signed or unsigned with modular arithmetic. So we'll define byte to be byte.int. C string will be a separation logic predicate that we can just define, although this one comes in the verifiable C standard library. You can have a C string with ownership share SH that represents a certain list of bytes, S, at address P. And it's an array. So here's an array of signed character. Why do we pick signed character instead of unsigned? Well, because the C compiler that we want to be compatible with represents characters using signed characters. And its length is, well, the length of S plus 1 to represent, space for the null character. And then we will take this list of bytes, concatenate the byte.0 at the end, map vbyte on that. vbyte is just a integer value. We have to convert the 8-bit byte to a 32-bit integer and map vint over that, so that's just map vbyte. All right? And there had better not be a null character before the end. So we have to say this proposition that byte.0 is not in the string s. So it's just math hacking, right? How else would you represent? I have a bunch of non-null bytes terminated by a null byte in memory at address P. And now we can represent our linked list. And this list cell is very much like any of the linked lists we had before. It's got a data at. It represents a T cell, which is struct cell up there. So it's got to have three components. The key pointer, which is a pointer value. The integer representation of the count. And next, which is another pointer value. And it's at address P. And we have a malloc token for P in case we want to free it later. But now each element of this linked list owns its own string. So we have another separating conjunct here, the C string at address KP representing the list of bytes key. So that's a list cell. And then the list, at address X, we have something that represents this list of pairs with a key and a count. So the values in our list are these pairs of string cross Z. There are three elements in each struct, but the third one is implementing the linking. Right? We want to say that this linked list represents the list of values that's everything but the last pointer. And so that's just, well, if sigma is not null, then it's got a key S and a count C const with the rest of the values being represented. And there exists a tail pointer Y such that X is a list cell containing S, C, and Y separated from the rest of the list rep. So look at this pattern. List cell is our abstraction of this three components, the C string, the record, the struct that's separate from it, and the malloc token. And here I put last the argument P that's the address of where the thing sits, and the rest of the components are sort of the abstract value being represented. Here we have list rep. Its last argument is the address at which the thing sits, and this list of string cross Z is the abstract mathematical value being represented. So this is a useful pattern to follow. Not that there's anything so special about having the address last, but once we pick a convention, then you can read separation logic definitions more easily if you know that first comes the abstract mathematical value being represented, and then comes the address at which it sits. And even C string itself is a definition of a separation logic predicate with the address last and the abstract mathematical value here. And if you want to parameterize your things over shares, so if you put in a readable share, this gives you enough permission to read from the string, and if you put in a writable share, this gives you enough permission to write to the string, and so on. But in this list cell and list rep definition, I didn't bother. I just filled in the top share for the C string and the data at here. Okay, so we could make a hash table with external chaining. Right? This is sort of the standard hash table that I teach to the sophomore software engineering in C class. You take your key, you hash the string to an unsigned integer value. You take that value mod the size of the hash table, mod n in this case, and that gives you a bucket that's a linked list. You can search down to look for the key and return the binding. So, how do we represent this? We have what's the abstract mathematical value we want to represent? Well, there's two ways of looking at the abstract mathematical value. The most abstract way is it's a finite map from strings to integers in this case. And that's really what the user wants to see. But it's often convenient to do our proofs in two levels. Let's prove that the C program refines a functional program, and the functional program has the sort of abstract mathematical properties we want. So in this case, we would make a functional program that operates on a list representing the array of buckets of lists representing the contents of these linked lists. Now, that functional program is in a certain way kind of pointless, because the whole point of a hash table is you get constant time access to the buckets in the array. And if we implement this by a list here instead of a constant time access data structure, then each access to the functional implementation will take linear time rather than constant time. But that's okay. The functional program is just a model for what the C program is doing, so that then we can prove the properties of the model independently of messy proofs about C programs. So let's assume we have a Galena implementation of insert and lookup on this functional model of hash tables. We still have to represent the data structure in C memory. That is, the separation logic predicate that represents this data structure. And so that would look like this. A hash table contents is this list of string cross C, a list of buckets. At address P, we want to represent this contents. Well, somehow implicitly in the middle of this data structure, we also have an array of pointers, right? All of these linked lists have addresses. And so for each bucket, we need to know not only what's the abstract mathematical contents of that linked list of the bucket, but we need to know what address that sits in. So to handle that, we will have an existentially quantified variable, the bucket list, BL. You can see what's on my bucket list. And it'll be a list corresponding to the buckets. So the length of this list will be exactly n. And in each place, we'll have the contents of the linked list first, the string cross Z, list of string cross Z, and the value, the address at which this sits. And then we want to enforce that the contents that we're supposed to be representing, this list of string cross Z, is the same as taking the first element of every element of this list. So to match up this string cross Z list with that string cross Z list at each bucket. And then let's see, the at address P, we have the pointer to this struct hash table with one field. And if we take P dot buckets, that's an array. So that's saying start with address P and take this path of this access path that goes struct field buckets, right? So that's the buckets array, and the field at. So field at is just data at, where you get to put in an access path. So it should say that at that address in that field there is some value being represented, and that's the value, right? It's a sequence whose length is exactly the same as the length of the array P arrow buckets, so therefore n. So the map second of BL is this list of addresses. So in each bucket, the address is the second component, and we use it here to say it's found in this slot of the array. Okay. And now we need all of the contents of the linked lists. We need all of those linked lists. So there are n of these linked lists. Some of them may be null. And we want the big star, the iterated separating conjunction of all of those linked lists. So here's the iterated separating conjunction of BL. What's BL? It's this list of pairs. And if we think about listrep takes two arguments. It takes the string cross z, that's the abstract mathematical value being represented, and the address, that's the place where that linked list starts. So if we apply uncurry listrep to one element of this BL list, we get the representation and separation logic of one linked list. So it's the iterated separating conjunction of uncurry listrep applied to this list BL. Okay? And we have a malloc token for the outer data structure so that when we want to free the entire hash table, we can free that one too. So there it is. It's just composing the operators we already have of separation logic to express some data structure. Let's talk about this append function. Append is going to traverse the linked list, keeping the t pointer exactly one behind the u pointer, so that when the u pointer is null, the t pointer points at the last element in the head list. And then, right here, we can say t arrow tail gets y to assign y into this field. And that will splice the two lists together. So this is imperative list append, just as you might expect in a C program. And so let's think about what the loop invariant looks like in this while loop right here. At some point, we've moved t and u. T is always one behind u, partway down the linked list. So there was the original sequence sigma, that was what x represents. There's sigma 3, which is what the linked list y represents. And then we'll take sigma. Sigma is going to be sigma 1 concatenated with h concatenated with sigma 2. Right? So that's the sequence concatenation part of the loop invariant. And t is a pointer to a single record containing h and y. And u, this should be a y here. Let's just make it u here. All right, so t is a pointer to a record containing h and u is a linked list representing sigma 2. So this separates from that, right? There's a separating conjunction, and that separates from this. And now the question is, how do we represent this component? There's a linked list that starts at x, continues for a few cells, and has a pointer coming out towards t. And whatever that is, there's a star here. It has to separate. It cannot overlap in memory from this. So we can't simply say x is a linked list, because a linked list goes all the way to the null pointer, and it would overlap with the linked list starting at t. So we want to be able to say that x is a list segment, right? That x to t, the pointer coming in at x and leaving as t, is a list segment whose sequence of head values is sigma 1. So, and this, remember, is how ordinary linked lists are represented, right? Either sigma is h con sigma prime, in which case we have one data at separated from the rest of the list, or p equals null.